Hi guys, and welcome back. So we previously ended the discussion where we discussed the gradient as the rate of change, and we were talking about the influence of the sign. Okay, so we figured here the sign. Well, we had 3/5 as the value for change. Okay, and here when we did the arithmetic, we got the sign, more information, in other words, that said to us, well, this is actually a decreasing change, a declining change, whereas that is an increasing change. Okay, that is a very important concept, guys. You're gonna get straight line graphs. You're gonna get a line like this, and they will ask you describe the gradient. Okay, and you must be able to tell whether it is increasing or decreasing. Okay, so never confuse that. All right, let us quickly look at the gradient of these two lines here. At this point, you may not really tell unless, of course, you start looking at the change in y over the change in x. And that's exactly what I'd like us to do here. Let's quickly put down the coordinates for each point, and then we discuss that. Here the coordinates are 2 and 10. Here the coordinates 8 and 10. Here we have 5 and 5. And down here we have 5 and 1. Now remember how we write our coordinates. Always x and y, x, y, x, y, and x, y. That's standard. That's how we roll. Now, the question then is, what will be the gradient of this line? Let's go back to our definition. Changing y over changing x. We know gradient is that ratio, okay? Now let's look at the coordinates. X here is 2, x there is 8. Is there a change? Definitely there is a change. What is the change? If we can look at 8 minus 2, it is 6, okay? Or you could have counted 1, 2, 3, 4, 5, 6, okay? Fine. Let's look at y. Is there a change in y? No, there's no change. 10 minus 10 is 0. So there's no change. 0 means nothing, right? It represents nothing. So you realize that then the gradient of a line that is very straight, not just straight actually, a line that is parallel, yeah, that's a good word to use in this case. The line that is parallel to the x-axis. Okay, here's my x-axis. Remember, my x-axis move this way, and this line seems to be moving that same way. Okay, so this segment here is parallel to the x-axis. So there's a conclusion here that we can make, because trust me, even if you were to find the gradient between, let me call this point K and that point L, okay, even if you were to look for the gradient for this line, I promise you, you will find that the gradient is 0, because there's not going to be change in y. The y coordinate for this point is 7, and the y coordinate for that point is 7. So that's a very important fact that we need to establish here. Gradient of a line, any line that is parallel to the x-axis, guys, is 0, because there's no change in y. Let's come to this one. This line is parallel to the y-axis. Okay, hope you can see that. So let us establish something. What about a gradient that is always parallel, the gradient of a line that is parallel to the y-axis? What can we say about such lines? Okay, and yes, it doesn't matter whether this line is on the positive y-axis or on the negative y-axis. The gradient should be the same. The same thing here, guys. Doesn't matter whether it is on the positive axis or the negative x-axis. The gradient will always be 0. Okay, very, very important. So let's look here at the change in y and the change in x. There is a change in y here because the y values are different. So it is 5 minus 1, and that is 4. Okay, I meant to write a 4 there. So this is a 4. But is there a change in x? No, there's no change in x. 0. But what is division by zero in mathematics? Do we ever divide by zero? No. We know that division by zero in mathematics is undefined. Okay, that is why we say the gradient of a line that is vertical or parallel to the y-axis is undefined. As a matter of fact, if you think about the gradient as a slope, let's bring this in more much practical life. Can you walk on a line that is parallel to the y-axis? In other words, can you walk on a wall? Unless maybe you're Spider-Man or something like that. No, you can't. That is why the gradient is even undefined. Do you see how this makes sense in real life? Yes, maths is really an application of what is going on in life. What we do in maths, we try to figure out why things happen the way they happen in real life. Okay, if you look at this one, this gradient is parallel to the x-axis. So think of the x-axis as that floor in your bedroom or that floor in your classroom. Okay, can you walk on the floor? Yes, the gradient is zero. And as a matter of fact, it's not just a matter of walking, but how smooth is it to walk on that floor? How nice is it? How convenient is it? You don't get tired. You can walk actually at a constant rate. Now let's think about this positive gradient here, or this increasing change here. If you were to walk up a mountain, would you get tired easily, or you'd find it enjoyable? You would actually find it a little bit difficult. It will be easy as you start. It will start to be, you will then start to experience difficulty as you go up the slope. Let's come to this decreasing change there. Okay? Between going up the mountain and going down the mountain, which way is easier? Obviously, going down the mountain, you are almost using no effort when you go down the mountain. Okay, that's a simple real life application of the gradient. Okay, I call this there's what you call the slope man. Okay, that's what you call the slope man. Okay, there's the slope man, right? Positive gradient, negative gradient, undefined gradient, zero gradient. Okay, so I hope you guys have gotten this. I'm gonna leave it here, guys. In the next example, we're going to derive something very cool. Okay, we're going to come up with something very, very cool. So tune in.